So today's main topic is going to be inverse trig. But before we get into that, I wanted to do one more problem on trig equations, just to warm up our brains a little bit. Remember all the techniques we've been working on in the past few days. So there's my little trig sheet. That's all I'm going to write down today. We are going to still use everything, all the Pythagorean identities and cofunction identities is all still hold. Hopefully you guys are getting those in your brains a little bit more now. Write those down if you need to, or pull up your previous sheets that you've written down. So let's take a look at IC 21. We weren't able to get to this on Monday, but it is all a bunch of trig equations, and they get progressively harder, or at least progressively different. And I, the second to last one, basically has almost everything that we could throw at you in terms of these trig equations. So we want to solve 2 sine squared x plus 3 cosine x minus 3 equals 0. So remember our steps that we wrote out. These equations have 3 parts. First part, we want to be able to isolate trig function equal to a constant and break it down into a series of equations, trig function equal to a constant. And then the last step, if we have some sort of different argument, 3x is here, or if you even look at j from this problem set, there's a 3x plus 1 inside of a cosine. So that'll be the extra add-on stuff that we have to do at the end. Or if the question says something like find the first 4 positive values or find values within a specific range, then we'll have some extra work to do at the end. So to save ourselves some of the time, let's go ahead and work through parts 1 and 2 for this problem, and we'll just leave the solutions as the general solutions. So we don't have any wonky arguments going on there, so we won't have anything to do in part 3 of these types of problems. However, part 1 is going to be a little difficult. So getting to the point where we have trig function equal to a constant is all what part 1 is about. And this is where all your algebra skills and all your trig identities incorporated with these algebra skills come into play. So the examples we've seen so far were factoring. Factoring is a major, major one. And you have to remember essentially everything that we can do in terms of factoring. First thing we look for is, well, is there a common factor? So is there some function or even constants we could factor out of every single term? And in this case, there's not. So it adds a little bit of a problem here. We do have the equation set up where it's an equation equal to 0, which is always good. That was kind of one of the first steps that we saw on Monday. We like it when we have things set equal to 0, particularly if we're looking to factor. So what can we do here then? Things we want to look for. This is one of those tricky ones where it's almost a quadratic, but not quite. If this were a cosine, it'd be cosine squared and a cosine, and then 0 power of cosine. So it would be one of these hidden quadratic equations where we might have to use a u sub to solve it. So the thing we're noticing is that, well, we have some diversity in our functions here. And this is one of our goals, or at least one of our problem-solving tips, is that sometimes we want to reduce the diversity of functions we see in the problem. And we can always relate tangents to sines and cosines and vice versa. And in this case, well, I only have sines and cosines, but since we can't factor anything, perhaps the best thing we could do is try to convert either of the sines or the cosines to the other. So then we would just have one trig function appearing in our problem statement. And primarily the sine squared we can use as a part of the Pythagorean theorem to convert into cosine squareds. And once we simplify that, We have only cosines. Let's go ahead and write it as minus 2 cosine squared x plus 3 cosine x minus 1. So we add our constants together, do all of our algebra, all of our simplification. And now it's as simple as we can get it at the moment with any sort of trig functions. We only have one trig function appearing, cosines, and you have to be able to recognize that it's cosine squared, cosine, and then cosine to the 0 gives us that constant. And so if we make these fancy substitutions, saying u is cosine of x, then our problem is really just a quadratic equation. And we can use all of our methods for quadratic equations to solve this. So you can use the quadratic formula if you'd like. I'm going to go ahead and multiply both sides by a -1. So it's going to flip all of the signs on the left. 0 times -1, still 0. I'm going to do that because we want to factor this guy. So 2 times 1 is 2. And so we're looking for factors of 2 that add to 3. So it's going to be 2 and 1. So we'll have 2u minus 1 and u minus 1. We set each of those terms equal to 0. And then now back substituting, we arrive at our most basic trig equations. We're looking for angles that satisfy cosine of x is 1/2 or cosine of x is 1. So that was part 1. A little lengthy there. But now we're just on the part 2. Part 2 is where all of our trig comes into play. So how do we solve this guy? We have a reference angle where the cosine is 1/2. So what's our reference angle? Pi over 3. Cosine of that's going to give me that 1/2. It's a positive ratio. So what quadrants are we going to be in? Cosine is positive in quadrants 1 and 4. And so we are looking for an angle here and an angle here. So what are we going to get? We're going to get x is equal to, first one's easy, pi over 3 has the same angle as the reference angle in quadrant 1. And then quadrant 4, how do we get this guy? We can go all the way around the circle. 6 pi over 3 minus 1 is 5 pi over 3. And then our last step, just add on the periodicity factor. Cosine of x equals 1, we still got to solve this equation. That one, just remember that when sine or cosine are equal to 1 or 0, it ends up being one of the degenerate triangles. So we need cosine x equals 1. It's actually going to be this triangle here, so a 0-degree angle. since cosine of 0 is going to give me that 1 over 1. And so x is equal to 0 plus the periodicity factor. And so that's the only solution for that guy. Any questions? Okay, so let's talk about inverse trig. So where do inverse trig functions come about in this problem-solving process, and how are they related? At least, how is simplifying these expressions related to the problems we were just doing? So we didn't have a time yet to talk about the graph of trig functions. We'll talk more about this in the next week or two, I think in 2 weeks. So I'm just going to add the graph. I'll talk more about how to graph it once we get to that section of the book. In general, what I like to do is split the function, put 4 tick marks on one side, 4 tick marks on the other, and then sine looks like that. And so what do we want to do? We want to create an inverse function to sine. But if you think way, way back when we first introduced inverse functions, in the first couple weeks of class, what is necessary for a function to be invertible? Necessary and sufficient. It needs to be 1-to-1. Namely, it needs to pass the horizontal line test, which we don't pass at the moment. Sine is not a 1-to-1 function. So what we have to do is restrict the domain. So I didn't label it. Each of these tick marks are pi over 2. So you can think each tick mark is a quadrant. So this is 0 to pi over 2 is quadrant 1 values, pi over 2 to pi over 2 to pi, quadrant 2 values, pi to 3 pi over 2, quadrant 3, and then 3 pi over 2 to 2 pi, quadrant 4. So what do we want to do? We want to include all of the values sine can obtain. So the range of sine is between -1 to 1. But we also don't want to leave any gaps. So one thing we're going to include, we're always going to include quadrant 1 because we like quadrant 1. All of the trig values are positive in quadrant 1. The values of the angles in quadrant 1 are 0 to pi over 2. Those correspond with our reference angles. So we like it when things start out in quadrant 1. But we also need to include in our domain values so that sine will be negative. It will obtain its negative values. And so we don't want to keep going into quadrant 2 because then, well, sine is still positive. It repeats all the same values in quadrant 2 as it does quadrant 1. So we're actually going to include quadrant 4. However, we're including the negative value of quadrant 4. So of course, we're again back in quadrant 4 over here, but we want our domain to be connected. We want to connect the domain, a continuum with all of the values. So we define our restricted sine with a domain of minus pi over 2 to pi over 2. And we want to include those values at the endpoints because that will give us the peaks in the range, the values of -1 and 1. And now when we restrict sine to that, well, just within that green line, we just have this as our function. Now it's 1-to-1. We're ignoring everything else. So now we have a 1-to-1. We can create the inverse. And we call that inverse sine, which we write as sine with this -1 in the superscript. Sometimes you also see it as arc sine of x. So arc sine just means inverse sine. And what's going to happen, as with all inverse functions, the domain and ranges flip. So now our domain for arc sine is -1-to-1, and the range is -π/2 to π/2. So important things to note. The input is an angle for any trig function, right? We compute the sine of an angle, the cosine of an angle. The input is the angle, and the output is the ratio. We are computing the sine ratio. So we get back a ratio of the side lengths of a corresponding right triangle. We flip that for inverse trig functions. So the input of a inverse trig is the ratio, and then the output is the angle. So inverse trig functions ask, if I give you a ratio, which angle has that sine ratio? So let's do an example. Let's see. So let me pull up the in-class activities. So I see 22. Let's take a look at D. 1D. We want to simplify y is equal to arc sine of negative square root of 2 over 2. So remember, this guy, the whole output is an angle. And a different way of phrasing this is we need sine of theta equal to negative square root of 2 over 2. We're looking for an angle whose sine ratio is negative 2 over 2, square root of 2 over 2. But it's a little bit simpler than what we were previously doing. So we should recognize this equation now. This is a trig equation. Sine of theta equals negative square root of 2 over 2. These are the basic trig equations that we started with. Trig function equal to a constant. But what's different about this? The difference is that we don't need any periodicity factors. We only want one answer. We only want one solution, because arc functions, they are functions, should only spit out one number. Whereas in a general equation, we're looking for the set of solutions that will satisfy that equation. So now we are just computing the value of a single function that corresponds to this statement, given the restriction that, well, I guess let's not say it's given that we deduce is in what quadrant. So theta should be in which quadrant? Where is sine negative? Quadrants 3 and quadrants 4. But by our restriction, the only range where sine is negative will be quadrant 4. And specifically, it's just a negative angle in quadrant 4. So pull up your reference sheet. We can draw it real quick. Which angle has a sine ratio of square root of 2 over 2? I'll give you a hint. If you ever see square root of 2's and you can't actually compute it, it's going to be your 45, 45, 90 triangle. It's the only triangles that have square root of 2's. If you ever see square root of 3's, it's going to be your 30, 60, 90 triangle. And so we need a pi over 4 reference angle in quadrant 4. And so it's just negative. In other words, arc sine of negative square root of 2 over 2 is equal to negative pi over 4. Since if I were to compute the sine of negative pi over 4, we would get negative 1 over square root of 2. And then if we rationalize the denominator, we will get back that negative square root of 2 over 2. So just be careful with how the numbers appear. Hopefully that's not too unfamiliar with you guys. So that's all there is to it. It's a bit more simple than the trig equations because we can essentially phrase each of these as a trig equation. But instead of solving a general solution, we're really only looking for solutions in a specific quadrant, one answer in one quadrant. So let's go ahead and define our inverse functions for cosine and tangent as well. So cosine starts at a peak, and it's going to alternate. And so again, we want to include quadrant 1 because cosine is going to be positive there. But we also need to include where cosine is negative. And we don't want to include quadrant 4 because cosine is positive there. So instead, we are going to restrict cosine to this domain from 0 up to pi. So cosine of x with our domain from 0 to pi, range still gives us -1 to 1. Then the inverse function, which we also call arc cosine, will have the domain and range flipped. So again, domain is -1 to 1, and the range, 0 to pi. So cosine is going to be the odd one because it's the only trig function that we're including values in the second quadrant. Tangent will actually have -pi over 2 to pi over 2 as well. So let's do tangent real quick. Tangent of x is weird function because it's got these asymptotes. And it looks like this. With the asymptotes being at odd multiples of pi over 2. So again, it's not one-to-one. However, if I just include one of these lines, one of these curves, it will be one-to-one. So we essentially just restrict tangent of x to a domain of minus pi over 2 to pi over 2. And for tangent, we need to include round brackets. We can't include the endpoints because it is undefined at those points. In the range, it's going to be all real numbers because it's asymptotic. So this tells us that arctan, or inverse tangent, is going to have a domain of minus infinity to infinity and a range of minus pi over 2 to pi over 2. So again, with these inverse functions, the input is a ratio, and we are looking for the angle. And tangent, because it's relating the opposite and adjacent sides, the possible ratios that tangent can obtain are between minus infinity to infinity. And it will achieve all of those values when the angle is between minus pi over 2 to pi over 2. So let's get to a couple examples real quick, and then I will give you guys some time, maybe 10 minutes here to try to get through a couple of these problems on your own. We did one from part 1. Let's do one from part 2. And so this is still IC22. It's the one we want to work on today. And let's do 2a. Is sine of arc cosine of 1/4. We want to simplify this. Compute the exact value without using a calculator. So how do we do this? Remember, arc cosine is an angle. And what do we want out of this angle? We need a positive cosine value of 1/4. So where is cosine positive? Quadrants 1 and 4. But because we have an inverse trig function, quadrant 1. So general rule, if the input ratio for an inverse trig is positive, then the angle is in quadrant 1. This is why we like using quadrant 1. It works for all of the trig functions. So we're in quadrant 1, and what is special about this angle? The cosine of the angle should be 1/4. So essentially this statement just says that cosine of theta is 1/4. Is the equivalent of those two statements. That's just the inside of that. So cosine of theta is 1/4. We know we're in the positive quadrant 1. How do I find this third side? Pythagorean theorem. Square root of 15, sorry. So I guess we could have called it y. I know that y squared plus 1 squared equals 4 squared. Common mistakes, just make sure you put the sides in the right order. Sometimes students will do 1 squared plus 4 squared, and you'll end up with like a square root of 17. Just be careful of how you're labeling it. And if it helps, always, write out the full equation. Y squared plus 1 squared equals 4 squared. And then you can do the mental math if you can. So y squared of 15. And now what are we trying to compute? Sine of that angle. So let's do one more. Let's do 3D. So we want to simplify cosine of inverse tangent of x. So the problem statement might say something like, simplify the following expression. You should not have any trig functions in your answer. So we have a similar situation, except now the only thing is I don't know what ratio to put in there. That ratio is given as a variable, which means I could have an angle in quadrant 1, or the angle could be in quadrant 4. So theta could be here, or theta could be down here. And again, our theta is this inverse trig function. Inverse trig function outputs that theta. And what do we know at least about this angle? That the tangent ratio is x over 1. So the opposite over the adjacent side is x. And so the quadrant depends on, well, what is the ratio we're plugging in? Is it positive or is it negative? So if x is positive, we're going to be in quadrant 1. If x is negative, we'll be in quadrant 2. Or excuse me, quadrant 4. But regardless, what's going to happen when we compute cosine of this angle, no matter which position it ends up being? How do I compute the hypotenuse? We do the Pythagorean theorem. So 1 squared plus x squared, square root. And because the hypotenuse is positive, it's going to be the same on either triangle, square root of 1 plus x squared. And now we see what's going to happen when I compute cosine of this angle. Well, it doesn't matter if the angle was in the first quadrant or the fourth quadrant, because cosine is going to give me the adjacent side of 1 and the hypotenuse of square root of 1 plus x squared. And this is how we would simplify that. Notice there's no more trig. We essentially just have a rational expression in terms of x. Any questions?